I want to kind of give you a short story about climate change, as well as about how we are constructing our climate models and how we're sort of using those climate models for, oops, let me back up here. Okay, this is a brief history of climate observations and modeling, understanding of past climates and the prediction of the 20th and 21st century, and then to discuss a little bit about computational methods. I won't go into detail about that because it is a highly technical area. And then I'll say something about the polar vortex, which everyone's wondering, why is it so cold? I'm not sure I'll be able to give a precise answer, but I'll give you at least my impressions. And the subject of environmental justice is connected to climate change and a very serious one, because some people are going to be more adversely affected than others. And then talk about public attitudes about climate change. And as you well know, this is a hot subject in which there's very strong differences, differences of opinion. Let me first start talking about the observational story, and I think one of the ways to start this story is to sort of look at the last 800,000 years, and here we've actually obtained the concentration of carbon dioxide from ice cores mostly, just right at the very bottom, or at the far end. Oops, I'll get used to this thing, excuse me. At the far right of this graph, the CO2 concentration is up to 400,000 parts per million. And the way in which we get the CO2 from ice cores is by examining the air that is trapped in the ice cores. And the assumption is it's the air from the time of the depth of the ice core. So you can go back to 800,000 years, and these big oscillations are essentially caused by orbital changes of the Earth around the Sun, and you're looking at going in and out of ice ages over that period of time. Now at the end here, we have very precise measurements from Mauna Loa, where it was starting to take observation in 1957, and it's gone up to 400 parts per million, as I said. And you can see that present concentration is much larger than the last time in 800,000 years. So one of the things that is often talked about as a possible other cause of climate change is the fluctuation in the solar radiation, which is received at the top of the atmosphere. And here we can only go back to sort of 1975, where the satellites from NASA started measuring on the solar radiation, and it goes through these 11-year cycles. But if you look at it carefully, and I'm not an expert in this area, but when you get this 11-year cycle, which is well known to the solar astronomers, but there isn't any overall trend. So generally, the people who are doing climate research say that the solar radiation isn't a strong factor. There is probably very small trends in here, but it's of the order of 0.1%. So it's fairly small in comparison to the climate forcing from increasing CO2. Now, if we look at the at the temperature change, globally averaged surface temperature, going from 1950 until the present, you'll see three different curves here. Sort of one curve is when you have El Niños. El Niños are when the Western Pacific warms up and along the equator. And usually when that happens, you get more of these red or these reddish colored or orange colored lines here. So you get on the warmest years in terms of a trend. And if it's a El Nino, it tends to be cold temperatures in the Western Pacific along the equator. And you get sort of more of a cooling effect. And we understand this fairly well. El Niños have been around for a long time, and there are going to be a lot of them even in the future. We haven't had an El Nino for a few years, but we're anticipating from early indicators that we're entering into an El Nino phase. So we can expect 14 and 15 to end up with a fairly warm year, and I'll show that in another way in a second here. There are two views on global warming: climate scientists and skeptics. Now, there are many different types of skeptics. There are credible skeptics who put forth a hypothesis about how they think it on the warming trends are actually coming about. And then there's the sort of the people like Rush Limbaugh who just put out ideas that have no real scientific basis. And the serious ones do a real service to us because they challenge us to make sure that we have got our facts right. And there's still some uncertainties, of course, in global warming. There's no question about it. For example, as we deal with clouds in our climate models, we still have a long way to go before we get all of the biases out of our cloud formulations and its interaction with the radiation. But there's other uncertainties, too, about how the oceans operate. We've made great progress from the early days of when I got started in the early 1960s, and we still have a ways to go, but clearly there's been progress. The skeptics often point out that there are some cooling trends. And I think in a noisy graph like this, you can always pick out a high point and a low point and say there's no global warming. For us meteorologists and atmospheric scientists and engineers, we look at the large trends and not on the fact sort of there's temporary hiatuses in the global warming. It's the overall trend which is the most important thing to sort of look at. Now some of these hiatus periods are, on the reasons for them, are somewhat unclear. It seems as though that as the globe warms up, there are certain decades or so where a lot of the heat goes into the oceans, and that's a factor. And also, in our climate models, we've only pretty much put in the largest volcanic eruptions. Now, the volcanic eruptions are very important because they cause sulfate aerosols to get into the atmosphere and reflect solar radiation back to space. And if it's a big eruption, you can clearly get a cooling that can last of the order of 18 months or 2 years after the eruption. But we also very recently, in an academy study, looked at the effect of the volcanic eruptions. And if you put those into our modeling calculations, we can account for some of the cooling events. on the order of a decade or so time scale. Now the same is true, and I won't sort of dwell on this. This is the Arctic sea ice extent, and as you probably noted in various publications and the newspapers, that the ice extent has shrunk a great deal, especially since 1995 or so, and it's still going down, and this is actually causing some dramatic changes in the Arctic, especially in northern Canada, Alaska, and Siberia. The danger is that if the permafrost starts melting, and permafrost has lots of organic matter in it, it releases a lot of methane. And that's happened in the very top part of the permafrost area. But some of these permafrost areas go down 30 or 40 or 50 feet, and maybe even further in some places. And there is deep concern about large releases of methane, and that's a very strong greenhouse gas. I want to show two satellite presentations. Here we're looking at in the orange or in the yellow color, we're seeing on the carbon dioxide concentration, and we're also looking at the vegetation. If you remember, the CO2 has a kind of a sawtooth increase as a function of time in the lower part of the atmosphere, and that on that sawtooth comes from the fact that in spring and summer, the CO2 is drawn out of the atmosphere and goes into the vegetation, and then in the fall and the spring, in the fall and winter, that vegetation decays and gives CO2 back to the atmosphere, so that we're able to observe it for the first time from a satellite, and this gives us a lot of regional detail about where the concentration of CO2 is coming from and how much. Now, this is going to be important, and if the world ever agrees on cutting back on emissions, we need to have somebody or some organization actually observing from satellite who is the largest emitters and who's not, so that we can be fair about dealing with an increase of carbon dioxide emissions. Another way of looking about it is the change of extremes, and here we show for decades from essentially 1950 up until the present that we're getting more record highs, those are heat waves, and fewer record lows. And so the ratio is roughly 2 to 1. So this is a way of looking at a trend in terms of cold records and warm records. Now, on the laws of physics and chemistry and the biology can be expressed in terms of mathematical equations, and those equations can be put into a form that can be solved by modern computer systems. And we include all of the physical processes that we can put into a climate model based upon our understanding. There are still some things that we don't understand as well as we would like. And then we put in forcings, and I'll point out the greenhouse gases, the volcanic effects, and solar variations as we carry out simulations of the 20th century and the 21st. The 20th century is very important because it's a way of verifying, are we getting the right answer? Now, I just show for the physical system, the fluid dynamic equations were essentially known in 1904, and this is the gentleman who wrote them down for the first time. V. Bjerknes, he was a Norwegian scientist. He made all kinds of important mathematical discoveries about these equations. And I won't go through this in any depth, except that these are the equations for momentum, for conservation of mass, and the first law of thermodynamics, and the gas law. I won't go through them in detail. Now, there was one gentleman, L.F. Richardson, who tried to solve these equations by hand. Essentially during the World War I, he was a Quaker, didn't want to take part in the war actively, so he was an ambulance driver, and I guess wars in World War I were kind of episodic, nothing happening, then a few days of coming out of the trenches and fighting, and then going back to not doing anything. So he had a lot of time, and he tried to solve this equation, this set of equations by hand using a mechanical calculator. And he wrote a book about it, a very famous book, and young people like me in the 1960s followed his methods, except he made a few errors in his calculation. And we since learned a little bit about how to solve these equations in the meantime. And so when the electronics computer came along, and on this gentleman here is Jule Charney, and at the Princeton Institute for Advanced Study under the guidance of John van Neumann, a very famous mathematician, they made a forecast with a simpler set of these equations. And it was a pretty good forecast. It was as good as any man or woman could do at that time. And it sort of led to the development of these models for forecasting the weather. Well, within a few years, in sort of 1955, 56, people started wondering, well, can we do the climate? And there was one calculation at on the first electronic computer showing, with a simplified version of what we have now, yes, you can get a realistic or somewhat realistic calculation. And so that launched on the beginning of climate modeling. And here I just want to show very briefly what's in a climate model. Here we have the sun's radiation. We have three different types of clouds: cumulus clouds, cirrus clouds, stratus or low clouds. And we include precipitation effects, either in the form of rain or snow. And we have snow cover. We have runoff into the ocean. We have vegetation. We have sea ice. In some of our models, we have the biological effects. We have land cover changes and currents in the ocean and so forth. And I'll show some examples of that in just a second. At the time I got started in the 1960s, we were just sort of working on atmosphere and simple land surface and ocean models. And we simplified things on purpose because the computers were so slow. It took us one day to calculate one day. And so one had to be quite patient. Now we can run on computers that have 700,000 or 800,000 processors. And we can actually do like the 5 or 6 or 7 years a day on some of the computers. So I won't go through all these, I'll just skip over here. So we have atmosphere, ocean, sea ice. I started coupling models in 1975. Sulfate aerosols, carbon cycle, dust and sea spray, and carbon aerosols. I'll show an animation of this, it's pretty neat. Interactive vegetation, so if the climate changes on the types of vegetation change, we keep track of like 30 or 40 different species of plants. the biochemical cycles, and now we're putting in ice sheets into our models. So on the evolution of these models is impressive. And we solved these. In the early days, we used latitude, longitude grids, but the problem is we had too much resolution up near the poles. So now we've gone over to things that are like this cube sphere, where it looks like a soccer ball, and it's nearly uniform resolution. And we use very clever numerical techniques, such as spectral element techniques, which are very efficient, that can be solved on massively parallel computer systems. And on the models that we're presently running right now have a resolution of roughly 25 kilometers over the entire globe. So you can just sort of see that we're down into the sub-county level, whereas before we only had maybe 2 grid points in Tennessee. And now we have like 30 or 40 or 50 grid points. And so with faster and more capable computers, we're able to do this sort of thing. And in the vertical, we have grid systems that follow the terrain, and then as we go into the stratosphere, we have pressure surfaces which go up to the top of the atmosphere. And I won't go through this in any detail. I just want to give you some idea of the land surface in our models. We keep track of all of the fluxes, sort of different types of vegetation. If you look in more detail at the hydrological cycle of vegetation, we have transpiration from the tree leaves, precipitation falling on the leaves, leaves falling off in the fall and the winter, and then evaporation, and then lots of layers in the soil, so that we keep track of the discharge of the water, not only from the surface, on the surface, but even from the water table under the surface. And this essentially shows on the vegetation changing. We included things like root litter, as well as litter falling in terms of leaves on the surface. And so all of this is integral part. And we work with a large group of scientists who specialize in all of these different areas. For example, land surface and vegetation effects and so forth. When we have a meeting once a year, and there's roughly 350 scientists who come. So the time I got started, there were 4 of us, and now it's up to 350 people. And we solve this on very large computers. The biggest one that we probably run on is at Argonne. It's a DOE computer. And we also run at Oak Ridge, at the Oak Ridge National Laboratory. And this is just one particular model that runs on 30,000 processors. Here I want to show a simulation of a very high resolution. This is 12 kilometers gridded resolution over the entire globe. And you're looking at the water vapor in the lower part of the atmosphere. And here you're picking up small-scale circulations. Every once in a while you'll see a hurricane, or here's one right here. Here's another one right here. Here's one going into the Gulf right here. And if you look at this in more detail, you'll see it has an open center, very realistic. And even kind of later on in this animation, you'll see the 2 hurricanes over here in the Pacific, and they rotate around each other. Here you can see it like that. And that's a very realistic effect. It's called the Fujiwara effect. It's been observed in the Eastern Pacific. Now, for the oceans, we can run that at roughly a 10-kilometer grid, and you'll see, for example, the ocean on the Gulf Stream going up and actually meandering as it separates from the coast. And you're getting wave structures right along the equator. And this is the Kuroshio current, which is very similar to the Gulf Stream over here. And if you look closely, you can see eddies virtually everywhere in the world's ocean. And even what's interesting about this is oceanographers haven't visited all these places, but they've gone here and they found the same currents that we're simulating in the real ocean in places that they hadn't observation fields. So that this gives a real demonstration of the realism that comes out of some of these high-resolution calculations. And that's why we're pushing to get faster and faster computers, and so that we can keep making progress. But I would say that in looking at this calculation, even looking at features kind of like eddies that are generated in Indian Ocean, such as this, which go all the way around Cape Hope into the Atlantic, are realistic features that you can see. And of course, where that airplane sort of disappeared is in this region here, and that's not an area that we have lots of observations. But we do know from even our modeling studies that you can get very strong eddy structures in that region, so it may be very difficult to find that airplane. Okay, now this one is a NASA animation from a modeling study, and the white areas here are sulfate aerosols from the burning of fossil fuels, mostly from coal. And that goes all the way over to Europe. Here we're seeing dust from the Sahara being swept across the Mediterranean. And these green areas are aerosols from the burning of fossil fuels, of the biomass, both in the Atlantic, over close to the Amazon and in Africa. And this white is from sea spray putting dimethyl sulfate into the atmosphere from the ocean. And so this is a simulation of essentially all of the main aerosols in the atmosphere, shown in a very dramatic fashion. And the interesting aspect to it for me is that you can get aerosols going long distances, for example, off the coast of China. Some of these aerosols go over Hawaii as well as into the western part of the U.S. And they're measured so that these simulations seem to be quite realistic in terms of the aerosols. Now, the aerosols are still a difficult problem for us to do in our models, because the aerosols interact with the clouds. And so you have a cloud interaction because many of the aerosols act as a nucleating agent on the cloud, so you get an indirect effect of the effect of aerosols. Now, in some of our models, we have high enough resolution that we can actually separate on different types of hurricane tracks. In the top three here, we have tropical storms. These are hurricanes, and these are very intense hurricanes. And you have these in the observations, and then from our modeling studies, we've also separated those, and you can see that we do go to have a sort of a reasonable distribution of tropical storm and hurricane statistics in our models. So we've only been able to generate these kinds of plots over this last year or two, and it really sort of generates another realistic feature that we didn't see in our lower resolution models. But when we go to higher resolution, we can get these very important tropical storms. And this is El Niños. Here's the observations on this side. This is the warming area in the Western Pacific, or in Eastern, excuse me. And here are the El Niños are the red, and La Niñas are in the blue. And here's what we get from our observation, the modeling. And we get a similar sort of distribution in this version of the model, and we get a little bit too strong of El Niños and La Niñas, but the frequency and the time of the year is pretty much simulated well. In our earlier models, we never got these things because they were too viscous, but we went to higher resolution and we were able to get them. Here's a standalone sea ice model. This is for Greenland, and you can see, this is in meters per year for the main streams in Greenland, and this is the model calculation. So we do a pretty good job of even simulating on the main ice streams over Greenland. So we haven't fully coupled on this sort of glacier model to our modeling system, but we're likely to start doing so over this next year. So this is what we essentially get by the end of this century, this 2100. This is the map that we think that we're going to find, and it essentially shows most of the warming taking place over the land and over the northern hemisphere where we have more land mass, and that it's going to be largest in the wintertime, and then a smaller amount of warming in the summertime, and we understand the reasons for that. And so this will be the planet that we'll be looking at in terms of warming. One of the things that we discovered, and I probably should be ending pretty soon, is that with our high resolution models, we've been able to understand a little bit better about heat waves. It turns out that there's a wave number 5. In other words, 5 waves around the globe, and those waves, from theory, slowly go westward. Okay, on the retrograde. On normal storms, which are smaller scale, go eastward. And we've been able to calculate these waves, and that they essentially tell us that when to expect a heat wave, because when this very slow-moving westward wave gets into a certain phase, it can actually give us some indication of, are we going to have a heat wave? And so I think that's a very useful thing for people to sort of know. And the modeling of the future, there's been lots of different suggestions about how climate's going to change. Right now, we're on this, what we call an RCP, and I won't go into discussion of what RCP is. But you can see these are observations of carbon emissions. And if nothing is done, we're going to end up with a much warmer planet. And it's this red line that we're going to end up. So you think about this, are we going to be able to sort of deal with the very toughest problem of cutting back on carbon emissions? And if we don't, it's going to be quite a different planet. There are some things that we can see in our modeling studies as well as observations, and one of them is that as we warm up the planet, we get observations of the increase of precipitation intensity. In other words, it's going to rain harder, and it's going to rain more. And this is going to cause, in some areas, flooding. And so this is something that we've already sort of known about in terms of the basic elements of climate change. Is you warm up the ocean, the ocean evaporates more moisture, there's more water vapor in the air, and that gives on the source of energy for storms. And we're seeing that happening more and more. Let me skip that. Now, let me tell you a little bit about the unusual year of this last year. In other words, the solar vortex. This is the annual 2013 surface temperature distribution. And you can, if you look at it and sort of take an eyeball, it's actually more warming than it is cooling. But you see this persistent cooling right here, which is a kind of a stationary pattern. Now, the stationary pattern affected Europe quite a bit because England had unusual heavy rains in the wintertime and the fall, and we saw Australia had very hot weather, so it was a record year for Australia. Now I want to turn to sort of last year. Our January of this year, excuse me. You can see this unusual cold area over here in eastern U.S. But it was unusually warm in the Alaska and the West Coast. And then elsewhere, there was a lot of warming. There's some cooling, but it was mostly warming. So on the record ones are in the deep red for that sort of month of the year. So when they, on the personal experience of people who live in the Northeast, is that this has been a cold year, but in general, it's been a warm year over the globe. And the Southern Hemisphere had its warmest record, and the Northern Hemisphere the fourth highest, even in spite of the fact that there are certain places where it was cold. But this is what you see almost year after year, is lots of noise in the pattern. But to talk about climate change, you have to look at the longer term average. Now here, in the typical November, we get a polar vortex over the Arctic, and where you get very strong winds and cold air. On this year, we've got more of a pattern like this, where it's essentially warmer on the West Coast and cold on the East Coast. And this has been very stationary. We have storms coming through, but it's been more on the cold side. And we don't really understand these permanent or these quasi-permanent stationary patterns. If we did, we would be able to make a long-term forecast for the season, but some seasons we can make forecasts out to 3 months in advance, and it's useful, but for some of them we can't. So this is an area of active research by a lot of researchers in academia as well as in the federal establishment. And I just want to sort of mention environmental justice. I think issue for all of us. And climate models can contribute to an understanding and the predicting of climate change. And this involves possible impacts on climate change, on food production, flooding, drought, sea level rise, health, and decision support. And higher the resolution and more complete models will help, and I feel pretty confident about that. Now, worldwide, on the weather catastrophes have increased in numbers, and here we're looking at the climatological events, hydrological events, and meteorological, and you can see that there's been a dramatic increase in the number of these events. And this has had infections on insurance rates. If you go to Florida, you might be paying as much for your house insurance as you do for your mortgage, in some cases even more. And if you look at on weather disasters in terms of dollars, you can see there's an increasing trend. Let me skip that one. I'm a little bit over time. Where are we with respect to climate change, mitigation versus adaptation? If we do nothing about greenhouse gases, then it's all adaptation. I think that we need both, that we need to deal with both. And models can provide vital information. All of these international conferences haven't really solved on the major aspects of the future climate change. And where is the U.S. going on climate change? The AAAS study, which came out about a week ago, asked on the question, or tried to answer on the question of why fewer Republicans believe in climate change than Democrats. I won't go into that. Now here's where on the climate scientists feel that it's human caused on the climate change, roughly 97%, and the American public is less sure about that, and there's lots of peer-reviewed research trying to figure out how humans are reacting to it. Now, there can be one easy hypothesis is that we haven't had enough disasters yet to get people's attention, which is, people kind of ignore scientific advice all the time. I mean, if you look at the situation of things like the vaccines, a lot of people are saying, well, we don't need vaccines. But for someone in my age group, we know that it helped with polio. I mean, polio used to be a very serious affliction, and that it could be easily cured now by I wouldn't say cured, but stopped and prevented by vaccine. So I think there's sometimes a memory loss about how things affect people. Now, in terms of public trust, I want to just end up by saying something about that. On the military is fairly high, the medicine is high, scientific community, Supreme Court are all fairly high. When you get down to the press, it's pretty low. The banks are low, and Congress is low. I'll let you make whatever interpretation of this data you want. There's great debate in Congress about the President's Climate Action Plan, which was announced just a few months ago. And I'll end, and I'll take some questions.
David Padgett. I'm the director of the Geographic Information Sciences Lab at Tennessee State University, and I've been involved with the AMS climate and weather studies education programs for about 10 years now. I have a question. With carbon dioxide being such a tiny, tiny, tiny constituent of the Earth's atmosphere, how can that tiny piece of the Earth's atmosphere cause this massive change that we're talking?
Well, first of all, on the way it works, and we can either demonstrate this in our models, our complex models, or very simple models, is that when the climate starts to warm up from that relatively small effect, and you get a enhancement, a very large enhancement by the oceans warming up, increasing the water vapor in the atmosphere, and the water vapor in the atmosphere is an additional large effect. It's what we call the positive feedback. And that positive feedback amplifies on the small CO2 increase. And we understand that fairly well, even with the most simplest of climate models, as a very large feedback. But we also get some feedbacks from, as we warm up the planet and we get less sea ice and less land ice, in other words, where you get seasonal change of the snow cover. And therefore, you can change a white surface to a dark surface, and you get a very strong positive albedo feedback. So these two effects are the largest two effects to amplify on the CO2 increase.
Solving differential equations depends crucially on the boundary conditions. I imagine your boundary conditions, land, temperatures, pressures, all kinds of other effects somewhere out in the atmosphere. We're doing simulations with the resolution of 12 kilometers.
Of
12 kilometers.
Yeah.
Do you have reliable data at that resolution? And whatever you start with some time coarseness, we hope that the initial surface is going to be crucial in what happens later. And for example, you have the polar vortices that you showed us in 2013, so different from one to the other, from typical to real on one date.
Right.
How do those affect the simulation results, like the videos that you showed us? How different can they be, depending on this boundary condition?
Okay, I probably should try to answer on that question in part, you know, if we talked out there. But I think it's basically on the land surface characteristics, we basically get from the Landsat satellite, so that we're able to put in the land model characteristics to get our model started. But then after we sort of run the model, we get sort of realistic changes in the vegetation types, and there's no problem of getting high resolution. On the Landsat data is, what, half a degree or something like that? I forgot. But it's much higher resolution than we use in our models. Our models sort of use a grid square, if you think about a square or a rectangle, and we can actually specify on the different types of vegetation in that square in a climatological sense. We don't actually separate where we have fir trees or deciduous trees on one side of the square. We just sort of make a mixture of the different types of the vegetation in that square and have that represented in our model. But I'm not sure if I answered your question.
What's the time step?
The time step is somewhere around 20 minutes to 40 minutes. So it's pretty short. We can do a pretty good job with the diurnal cycle.
Among the credible skeptics, what is the principal criticism or the hardest one for you to respond to And what's the effect of that possible criticism on the outcome of your models?
Okay, well, I think, as I mentioned, our major weakness, I think, is the clouds. We don't understand the cloud processes well enough, and how the convection works in the tropics and mid-latitudes. Now, as I was telling one of the professors this afternoon, we have established some sites, both in the tropics, mid-latitudes, and in the higher latitudes, where we have put instrumented, very careful measurement systems. We have towers, even have remote aircraft taking measurements and then comparing them with the satellites. And we find processes that are going on that we don't include in our models. And so there is some uncertainty about how we treat the cloud radiation interactions. And that includes in these aerosols I showed up here too. So there's an intense program trying to improve our understanding, because on the modeler, we have to rely upon our colleagues who know how to do these things in more depth than we do. But they have to have observations to improve on the way that we do it in our models. And so I would say that the cloud interaction with radiation is still on the biggest uncertainty. But there's other uncertainties too.
Let me start by saying thank you for your presentation. My question has to do with the urban heat island effect, and if your models take that into account, and do you think the effect is negligible, and if so, why?
We actually have some aspects of the urban heat island in our models, but you really have to get down to like 1 kilometer or even smaller to really accurately simulate that. Now it turns out that what we sort of have done is put in to our model the vegetation changes in the urban areas, and the fact that there's lots of asphalt, and that aspect. But actually, getting down to the details of the urban heat island require us to have resolutions of the order of 1 kilometer. And so on the way that we attack that is that we run our global models first, and then we sort of work with the regional climate modelers using the global model as boundary conditions, and so that they can really look in detail with very high resolution the versions of the model in these regional models. Okay?
I want to invite you to continue the conversation at the reception in the atrium. We have some folks who need to go. But a little thank you gift to Dr. Washington, and if you will join me in a round of applause.
Thank you. Thank you.